Hi, everybody. Thanks for coming. So I'm excited to present this opportunity that Intuitive Machines is sponsoring a thermal infrared spectrometer developed by the University of Hawaii and is going to deploy it on their first lunar communication satellite. So next slide. So this satellite should be launched next year, or hopefully the first half of the year. So this is a hurry-up project. It only started about 5 months ago. So 5 months from concept to we're delivering the instrument in a few weeks, and then it'll go on the spacecraft and be shot into lunar orbit next year. So this instrument is basically, it's called Lunar HiTi. HiTi is for a hyperspectral thermal imager. It's a derivative of a couple of instruments that were developed for NASA Earth Science Technology Office called HiTi. One was already launched in space. The second one is aimed for a launch next year in LEO. And these are, in fact, descendants of some DoD instruments that we developed over several years. So the instrument's designed to characterize the dynamics and distribution of water on the lunar surface, determine the mineralogy of silica phases at the lunar red spots as complementary lunar vice, characterize the mineralogy of candidate mantle exposures, measure 10 micron region radiance to support analysis, again, by instruments like on lunar vice, and finally measure thermal emission spectra on the night side of the moon where the soil emission is suppressed and the emission is dominated by lunar rocks. Next slide. So here's some basics. So there's a rendering of the instrument in the upper right. It's an imaging interferometer. It operates from 5 to 10.5 microns, the 10 wave number resolution. The resolution is defined by the TESS instrument. It was very successful around Mars. It's 640 pixels across track. The resolution on the ground at periapsis with the current orbit that we're working with is 240 meters, and it's a little over 2 kilometers at apoapsis. It's designed to capture the 6 micron band, the Christensen feature in lunar soil, partial coverage of Reststrelin bands due to the major lunar minerals, very high sensitivity radiance and permanent shadow, and then again, post-sunset measurements of surface rocks. It has much better calibration at 6 microns over the SOFIA experiments that we use to detect molecular water on the lunar surface from that airborne observatory. Okay, next slide. So the plot on the right shows the wavelength range. The upper limit is right. We didn't have actual library data that goes down to 5 microns, but this is just to show what the capability is. So the top 2 spectra are emission spectra of lunar soils, and the little bump you see around 8 microns, that's the so-called Christensen feature, which is a scattering feature that's proportional to the silicate polymerization of the soil on average. It emerges when in very fine grain sizes. When you have coarser grain sizes, you see very distinct spectral features, and the instrument is the wavelength range is particularly well suited for looking at high silica materials like amorphous silica and quartz. It only captures about half of the band of the plagioclase, clinopyroxene, and olivine, but still we'll be able to distinguish those materials. Next slide. Okay, here's the 6 micron band story. So the frame in the middle are a flock of SOFIA spectra showing 1 to 2% deep or high emission features. This is due to the HOH bend, which is unique to the water molecule. That feature is not present with hydroxyl bonded to any other cation, so we can unambiguously detect water. The 2 frames on the right, the spectra on the top are a series of water-bearing glasses that were produced by Shuai Li, and you can see that little bump just past 6 microns. That's the reflectance spectrum of these glasses at those wavelengths. And then we plotted is the 6 micron band depth versus the 3 micron band depth. You see there's a good correlation at where the 3-micron band depths are about 50%. And then the water kind of poops out, and that's because there's a phase relationship where at low abundances, water yields to hydroxyl when it's in equilibrium with gases. Next slide. Okay. I've magically hidden the things on the right side, but basically the SOFIA experiment we've shown on the regional extent on the left. If you use your infrared glasses, you'd be able to see that there's a strong latitude dependent of the water emission feature. The middle frame, which for those of you who have regular human vision, can see that there's an inverse correlation of peak height and temperature. And on the right, again, you infrared people can see that would see that there's a strong diurnal variation in the water abundance in the SOFIA data when we look at the global behavior. Okay, next slide. Next slide, please. Okay, the science objectives: map the distribution dynamics of the water molecule, exploiting our unambiguous sensitivity to H2O. Capture the Christensen feature maximum at silicic anomalies to identify the silicic phase that's actually causing these anomalies. Characterize the mineralogy of mafic anomalies that might be potential mantle outcrops. Measure the 10-micron region radiance in permanent shadow, which has a lot of reflected light in addition to the emitted light, so we can develop a correction that can be used for landed experiments. And again, exploit the post-sunset rock thermal emission to reduce the influence of soils at rocky sites. Next slide. So a version of the instrument in the upper right, and the magic all occurs in in the upper right. That's a little, about a 1 centimeter Fabry-Perot interferometer that produces interference fringes that we can turn into a spectrum. The way we collect data in the upper left is very similar to a linear variable filter spectrometer, where the imager is scanned across a surface, and for any particular pixel, it builds up a spectrum as we scan across the surface. The only difference for us is that we build up an interferogram, and then we apply a Fourier transform to get the spectrum. And on the bottom, that shows an interference pattern from a quartz sample, and then the quartz spectrum from the Fourier transform. Okay, next slide, please. Basic components: we got a lens on the left, interferometer is in a vacuum dewar, there's a cryo cooler. This is also a strain laser superlattice like Jorge's instrument, and camera and cooler electronics. This is actually the first prototype we built under DoD funding. Okay, next slide. Let's skip this because I see flashing lights over here. I see flashing lights all the time, but also over here. Here's the orbit of the satellite. It hasn't been finalized, but roughly it's very elliptical. It's designed to emphasize allow a long dwell time over the southern hemisphere for acting like a COMSAT, and then it goes much quicker and closer at periapsis. This is just showing that our field of view, we always see the moon, where the moon is always filling the field of view. Let's see what the next slide is. The orbit's inclined, but we can still see the pole with a tiny bit of off-nadir pointing. Okay, next slide. Okay, summary. It's a thermal hyperspectral imager provided by the University of Hawaii to IM in an inclined lunar elliptical orbit. Spatial resolution will vary from 250 meters to just over 2 kilometers. We'll map the distribution dynamics of the water molecule, capture the Christensen feature maximum and Rastrellan bands at silicic sites to identify that silicic phase, characterize the mineralogy of known mantle outcrops, and then exploit post-sunset rock thermal emission to measure the thermal emission spectra of actual surface rocks. Okay, next slide. Oh, okay, stop generating.